So let's go to the quantum mechanics and speak in very simple terms about quantum mechanics introduction. So everyone of you heard about quantum mechanics, especially about Schrodinger's cat, and this basic experiment that Erwin Schrödinger presented himself, rather this thought experiment. He told he wanted to understand the nature of the quantum mechanics, and he told that let's imagine an experiment. We'll close a cat in a box. In this box, we'll have a source, some radioactive source that will randomly decay and will randomly emit a particle. Once the particle is emitted, it will get detected by this Geiger counter, and if it gets detected, the source, this flask of poison gets smashed, and the cat dies. So, and what's the interesting thing about it is that according to quantum mechanics, until we didn't observe the cat, until we peeked into the box, we don't know what's the state of the cat. So, when we actually when we look into the box, we can say that, well, deterministically, the cat is either is alive or dead when we observe the box. But until we actually check the box, we can only say that cat involved superposition of dead and alive. So that's kind of the paradox of quantum mechanics that Erwin Schrödinger thought about. And here you see this equation that tells, it's called quantum mechanics. Schrödinger's equation tells about quantum mechanics. It's not really about the equation itself, but what it means. So here you have the wave function, and quantum mechanics, here the species is wave function, everything is a wave function, and there is no cats. So what's interesting about this equation, that it admits actually, it can admit one or can admit many solutions, but it can also admit superpositions of solutions with some kind of with some coefficients, A or B. So superposition is also a solution. So that's the reason you can see that if this equation describes the real world, that means that if cat can be in one state, it can be in second state, it can be in superposition also. So yes. So going back to the cat. So here you can see the cat, and until we observe actually the cat, until we observe the cat, we pick in the box, we can say that cat is both into superposition of states, so it can be dead and also alive. And here we have this kind of normalization factor that normalizes cat state. And what's important that we measure the state of quantum mechanics is actually by taking the square amplitude of the system. So what means we actually project the system to one of the states, either to the cat is dead or cat is alive. All right, so going back to more application, to our applications for quantum mechanics, we are interested actually in sending transmitting messages, and how we can do it in quantum mechanics. We can actually do it with tiny particles, but the most interesting way to do it is with photons, because well, photons don't really interact a lot with matter, and so that's the reason it's interesting to actually use the photon polarization to use in quantum communications. So here you can see once again that this wave function, which is superposition, can be superposition of both, for example, horizontal and vertical polarization. Well, it's a quantum state, and quantum mechanics would say we call it a qubit. So more, if we take analogy from classical communications, that would be 0 and 1. And well, until we measure actually the system, this can be imagined this qualitative manner as a superposition. What happens when you measure the system? When you project one of the states, it can be either horizontal or vertical polarization. So measurement, we say, collapses system into the vertical or horizontal polarization. And how we can measure for example, a photon. So we actually use every day. So for example, if you have even the sunglasses are a typical polarizer through which when you observe the light, you can see only one single polarization of the light. So you basically performing quantum mechanical measurements when you even wear sunglasses, because you actually detect some kind of specific type of polarization. So what's interesting that that superposition by itself is actually an absolute term. It's not an absolute term. What's very interesting in quantum mechanics is entanglement.